Okay, all right, we're good to go. All right, so everyone, thank you for sticking it out to the second to last talk to KubeCon, and being here to hear about our experiences with Apache OpenWhisk and putting it on top of Kubernetes. I'm Dave Grove. I'm an Apache OpenWhisk committer, and I've been one of the leaders of our community effort to take OpenWhisk and deploy it on top of Kubernetes. And it's my pleasure to be here today to represent all the people who did this work together and tell you about our experiences with doing that. Okay, in terms of the plan for the talk today, I'm going to start out with just a few minutes of a general overview of Apache OpenWhisk to give you an idea of the context in which this work is being done. Then we're going to dive down into some of the implementation and deployment architecture. In particular, we're going to look at the heart of the system, the critical path of invoking a function, and some of our container management alternatives, and what those mean for performance. Because that's really the sort of key to getting the performant and scalable system. And I want to tell you about some of our experiences with that and some of the alternatives we've looked at. Then we're going to shift gears and get into a demo mode. And I want to talk about some of our more recent work about going beyond simple functions, doing serverless composition of serverless functions. We're going to use that as a demo to show some of the tools we've been doing and some of the cool things we're doing and some of the future directions for the project. Okay, so what is Apache OpenWhisk? So Apache OpenWhisk is a production-ready open source function as a service offering. So it's got a number of pieces. There's a core fast runtime, command line tools, there are language runtimes for each of the supported pre-supported languages we have, and there are a bunch of packages that provide bindings and convenient ways to use common cloud services. Apache OpenWhisk is pretty aggressively polyglot. There's about a half a dozen languages that are sort of built in. You can write your functions in any one of these languages, but if those languages don't suit you, you can bring your own black box container. So basically, you can run almost anything you want as a function as long as it responds to a pretty simple HTTP REST API. The system is designed to be extensible and pluggable. Between most of our major components, we have these service provider interfaces, or SPIs, that give us a way to customize the deployment of this thing and make different choices for different people who are deploying it. It's pretty easy to bring additional language runtimes. Some of the providers have different runtimes deployed in their things, add additional packages, SDKs, and so on. There's also diverse ways to deploy OpenWhisk. You can deploy it on a bunch of container orchestration platforms, Docker Compose, Kubernetes, Mesos, OpenShifts. You can also use Ansible to just deploy it on a host of VMs or bare metal machines. There are hosted commercial deployments of OpenWhisk by both IBM and Adobe, and there are additional companies that are in various stages of getting additional hosted commercial deployments out. But OpenWhisk is also an open source project, so it's an Apache incubator project. There's a pretty active open source developer and user community, and as a whole, the project is working towards official releases and graduation from incubation, which we're hoping to have happen relatively soon as we sort of move up the curve to maturity. So it's in production already for multiple companies, but we're still an incubator project in the open source sense. So OpenWhisk on Kubernetes, what does this project entail? And really, there are three major stages of work. The first one was fairly straightforward. So OpenWhisk, the control plane of OpenWhisk was already containerized, and so getting that control plane to run on top of Kubernetes was really just taking these containers and deploying them as using Kubernetes concepts, stateful sets, daemon sets, and so on. In the process of doing that, we found places where the existing code wasn't really a great fit for Kubernetes, and so we did a bunch of adjustment to the OpenWhisk code base, to the actual implementation, the configuration and deployment scripts to make it a better fit for Kubernetes, to make it easier to deploy and do that. And the third stage, which is really sort of just in the initial early stages of it, is now that we're on top of Kubernetes, trying to think about how we can exploit Kubernetes capabilities to simplify the OpenWhisk implementation, give us less to maintain, more naturally fit into the Kubernetes environment, and so on. So all this work is being done in a sub-project of the Apache OpenWhisk project. The GitHub repository is incubator OpenWhisk deploy kube. If you go there, what you'll find is something that supports multiple versions of Minikube and Kubernetes. There's configuration files, readmes, and deployment scripts for deploying the system onto Minikube and single and multi-node clusters. And as of a week and a half ago, we actually have a Helm chart that will let you deploy it as well. And we're going to do a demo of this later. All right. But first, so what are the underlying assumptions for OpenWhisk? What are we trying to do? And some of these assumptions come around what we mean by production ready. So when we're building OpenWhisk, we really want to build a software stack that's capable of operating at very large scale, at public cloud provider scale. So many, many millions of function invocations a day. All of the core components in the control plane are designed to be replicated for fault tolerance and scalability. And we're also interested in building a multi-tenant system. To really make this thing economically viable, we need to deploy a system and then run code from many users on top of that. So we're dealing with running arbitrary code, including arbitrary containers that we haven't even looked at from many users, and then providing all the isolation and security, both to protect our control plane from those users and to protect the users from each other. Another thing about being production ready is when you take OpenWhisk and I'm a provider and I deploy it onto my cloud, it has to fit into the rest of my cloud. So it's got to naturally just plug in there, and that's why we have so many SPIs and plug points, so we can take the core code base, deploy it basically unchanged, but yet feel like we're part of the cloud platform on which we're plugging into. A second set of assumptions come from some of the workloads and use cases we're interested in supporting in OpenWhisk. We have a strong emphasis on extremely low latency and minimizing system overhead. And some of that's coming from the applications we want to support. We want to be able to run the backends for interactive applications on OpenWhisk. So the backends for mobile apps, for chatbots, and we also want to run applications where a single top-level logical action, something the user wants to do, will actually be a pipeline or composition that will spawn many function requests. And also because of the charging model of serverless, there's a tendency for short-running functions. And when you have short-running functions, it's harder to amortize the system overheads. Right? So you don't have as many places to hide. And so we have an emphasis on low latency and minimizing our system overhead. All right, so now let's dive into the details a little bit what happens when you actually invoke a function on OpenWhisk. So the basic OpenWhisk model is that every user function pair is going to be executed in a distinct container. Now we may reuse one of those containers, so a particular container may execute multiple invocations of its unique user function pair, but it'll only ever execute that function from that user. So given this model, container scheduling, caching, and reuse are really essential for us to get the kind of performance, scalability, and latency response we want. So what I'm going to do right now is walk through the life cycle of a user container. So a request comes into the system to execute a function on behalf of some user. We don't have a container for that yet, so we'll have to create it. All right, we refer to this as a cold start because creating a container can take a fairly long time. All right, so once the container is created, we can then initialize the container. So in OpenWhisk, most of the volumes of the invocations are actually using one of our predefined runtimes. So they're using Node.js or Java or Swift or Go or Python or PHP. They're using a language runtime. And so when we're creating a container, what we're doing is we're creating a container that's ready to run some code in a particular programming language, but it doesn't have the user's code in it yet. So in the initialization phase, what we do is we inject the user's code into that container, and then we call an initialization function to allow the user to prepare to actually execute their functions. This is where the user code has the opportunity to, for example, create database connections they want to cache, or do other kinds of initialization actions they don't want to do in every function invocation. Now, creating containers can be pretty expensive, and as I said, a lot of our workload comes from running one of our language runtimes, and so we have a notion of stem cell containers. And what the system tries to do is maintain a pool of these stem cell containers, Node.js containers, PHP containers, Go containers, whatever the provider has decided, that are ready to run. So here the language runtime is up, ready to go, and all that has to happen is we have to inject the user code into it, and we're ready to run. Now, whether the container was cold or pre-warmed, once it's initialized, the next thing to do is actually run the user code. So that's calling the run route on the container. This invokes the user function, it computes, it returns a result, and we return that to the user. Now, when the function returns, we actually leave the container running for a small amount of time. This is our grace period. Oops. And what we're hoping to do here is within this grace period, this relatively short amount of time, we're hoping another request from the same user for the same function comes in so we can reuse this container immediately. And that's our hot path. So here there's no delay at all. The request comes in, there's a ready container, it goes. After that grace period expires though, we're going to suspend the container. And this is really related to trying to run a profitable service. So our billing model for IBM Cloud Functions, for example, is we only bill the user for the time their function is actually running. So when the container is sitting there running, but the user's code is exited, we're not billing them for that. And we're billing them at about 100 millisecond granularities. So if we just left the container running for a long time without suspending it, clever users would have a function that came in, fired off some background work, and then a future invocation would then go and harvest the results of that background work. And users are clever. So if we didn't have the suspension capability, they would definitely be doing this. All right? So now the container's suspended. It sits there for a while, and another request may come in which case we resume the container, and this is a warm path. So here we've got a container that's ready to execute the code. All it has to do is be unpaused. All right, but the container may be suspended for a long time and nothing happens. When that happens, it's idle and it times out, And so we go ahead and destroy the container to make room for other containers in the system. So that's the overview of the user container lifecycle as we go from creation through actual use to destruction. Okay, so what I wanted to do now is take you through the critical path of a function invocation as it comes to the system, goes through our control plane, executes, and comes back. And in these pictures, my convention is that the blue boxes are part of the OpenWhisk control plane, green boxes are the user containers. Okay, so the function comes in, a request to execute function F with some parameters from some actor outside in the world. The first thing it has to do in Kubernetes term is go through our ingress. So the ingress does the SSL termination and then forwards the request to the appropriate controller. The controller's job controller has several jobs. One of them is if this is a blocking request, the controller is the part of the system that's responsible for maintaining the open HTTP connection. The controller also deals with all the authentication, authorization, and emission control operations that need to be done to make sure that we actually want to run this function for this user. And finally, it runs the load balancer. And the job of the load balancer is to try to select the invoker component, the invoker instance that's actually going to handle this invocation. So I'm going to go into a little bit more detail. So each controller is responsible for assigning work to a pool of invokers. And these invokers, in turn, each is managing a set of user containers that are in one of the lifecycle states we talked about before. So I've got my controller, it has a pool of invokers, there's some user containers, they're in various states, some of them are running things, some of them are paused, some of them are hot, ready for work. And the goal of the load balancing algorithm is to pick an invoker to run this, to minimize invocation latency, maximize system throughput, and hopefully find one with a warm or hot container for this particular function and user. Now, because we need to be fault tolerant and we need to be scalable, the controllers are actually replicated. So we have multiple controller instances that are sending work to this pool of invokers. So we have some replicated state in the controller. And the system is fairly large. So one of the challenges for our load balancing algorithm is dealing with the scale, the replication, and the rapid state change. And as a result, our experience has been that we actually are unable to use a centralized scheduling algorithm that has actually precise information of the state of the system. Things are changing too quickly to let those controllers have an accurate view of what's going on. So what our current load balancing algorithm does is heuristically uses hashing, a hash on the user and the function to pick an invoker to run on, and it looks at the invoker queue length to try to decide if that invoker is busy or not. And it does a round robin around those based on this hash function. And the hash function will try to help hit the locality. And the queue length will prevent us from overloading a particular invoker. But all of this is fairly heuristic because we can't know exactly what the state of the invoker is. There are too many of them and they're changing too quickly for us to know that. Now this is a place where we do have an SPI to enable algorithmic exploration. So if you want to play with OpenWhisk and you have an idea for something you think could do better, you could plug it in here and try it. So I encourage you to, after this talk, maybe try that out. Okay, so stepping back up to the flow of the function through the system, once the load balancer has picked an invoker, we enqueue it on a work queue for that invoker to pick up later. And we use Kafka for that. There's one topic for every invoker. Eventually the invoker will pull it off there and hopefully be able to select a container it already has to execute the request. If not, it has to create one. It invokes the action and waits the results. Once it has the result, it does two things. First, it immediately enqueues that back on Kafka to go back to the controller. After it enqueues it, it then asynchronously extracts the user container logs and forwards them to a logging service. So we have to get the logs out, but we don't have to wait for that to get the result back to the user. The result flows back through Kafka, back to the controller, and if it's a blocking request, then we return the result on an open HTTP connection. So that's sort of the path of a function as it goes in and out of the system. Okay, I want to talk a little bit more about the invoker, in particular how it's interacting with the underlying container engine. So this is another place where we have an SPI. It's the Container Factory SPI. And what this does is it gives us a pluggable abstraction for container engines. We currently have 3 implementations of this in the open source project. There's one that talks to Docker, one that talks to Kubernetes, and one that talks to Mesos. And when we deploy OpenWhisk on top of Kubernetes, we actually have the option of using either the Docker Container Factory or the Kubernetes Container Factory. What I'm going to do now is just explain what each of those look like and explain why we might want to use them. Okay, so the Docker Container Factory is the simplest one. In this setup, we allow Kubernetes to schedule the pods that represent the OpenWhisk control plane. So all those blue boxes, the controller, the invokers, Kafka, Zookeeper, or other system components, but not the user containers. From Kubernetes perspective, what happens here is we run the invoker on a daemon set as a daemon set on all the worker nodes that are labeled with the role invoker. And that's the only Kubernetes pod that's actually running on that node. What we do then is the invoker talks to the local Docker daemon on that node and does all the container operations for us. So as far as Kubernetes is concerned, there's just one thing running here, and we've tainted the node and the containers to prevent anything else from going there. And then the invoker talks to Docker, does all the container operations, talks to the user containers to initialize and run them. Okay, so that's not incredibly kube-friendly, kube-native, but it's a way of making things work, and it has some reasonable performance characteristics, which I'll talk about in a little bit. A second alternative, which we've been exploring, is the Kubernetes Container Factory. This is a much more Kubernetes-centric approach to running OpenWhisk. What we do here is now we're running a much smaller number of invokers, much smaller than there are worker nodes. We deploy those as a stateful set. The invoker talks to the Kubernetes scheduler to actually create and destroy the pods, the user containers. So now our user containers are proper pods. They can run on any worker node whose role is invoker. And so now we can have an invoker managing pods, managing user containers that are scattered across multiple nodes in the system. So the invoker can have a much larger pool of containers, and it calls the init run thing. There's one problem with this picture, if you've noticed. So Kubernetes doesn't have any notion of suspending a pod, right? So what I've lost now is I've lost my ability to stop people from stealing from me. And that's not so great if I'm going to actually try to run this for a profit. So the way we get around that is we add this notion of invoker agents. So the invoker agents are a daemon set. It's a small program written in Go. It runs on each of these worker nodes. And all the invoker agent does is it actually does the suspend and resume operation. So when an invoker needs to suspend or resume a user container, it talks to the invoker agent on the appropriate worker node, which talks to Docker and suspends the container. And it also, for efficiency, when we have the invoker agents running, we can also use them to extract the user container logs directly from the local file system without having to go through the Kubernetes APIs. Okay, so that's the three different options for the container factories. What I want to do now is talk a little bit about, present some experimental results and sort of look at the performance trade-off of these three options. And the goal is not to sort of say that, it's just to understand the current performance of our container factory implementations, in particular to understand the cold start latency, what are the different container factories, what does it do for that? What's our warm and hot latency, so what happens when I can reuse the container? And are there any throughput differences between them, and if so, why? So these experiments are done in a pretty small cluster. It's a Kubernetes 1.8 cluster with 13 nodes. I have 10 invokers, 2 nodes that are dedicated to run my blue boxes, my control plane, and 1 node that I use for a load driver. And what that load driver, by having the load driver as part of the cluster, I can eliminate any kind of external network variability than there's a driving load from my laptop. So for all the experiments, I'm going to measure the full path, starting with the ingress, going all the way through the flow. So ingress, controller, Kafka, invoker, Kafka, controller, back out. That's what the path we're going to measure. But we're going to use trivial and no-op actions because what we're really looking at here is trying to understand the system overheads. How low can we go? How fast can we go? And what gets in the way? Okay, so first talk about latency results. So here, the first set of results, what we're going to do is we're going to invoke a blocking function one at a time. This is the only thing that's happening on the cluster. So this is an extremely optimal situation. All we're doing is invoking one function again and again and again, 10,000 times in a row, and measuring what the end-to-end latency is as perceived by the user in milliseconds. And there's several things to look at here. So the first scenario to look at is the cold start numbers. And so to get these, what I did is I disabled all of our container reuse mechanisms. So every time the container comes in, a request comes in, we have to create a container. All right? And we can see here there's a huge difference between using the Docker Container Factory and the Kubernetes Container Factory. And this is the reason why as we're going forward to putting things into production in the first round of this, we're really looking at using the Docker Container Factory. 3x hit on cold start latency. Even with all the caching we do, and as good as the cache is, this is a big hit to take. So it's 700 milliseconds versus over 2 seconds. And none of this is Docker pull time. In this experiment, the Docker image is already on the worker node. This is at the time it takes to create the container and get it up and ready and responding so we can talk to it. Okay, a second set of things to look at is why is container reuse so important? So here, if we have a warm container and we're using the Docker Container Factory, our end-to-end response time for this trivial action is 7 milliseconds. It's all the way through our control plane and back in 7 milliseconds using the Docker Container Factory. Now, surprisingly, with the Kubernetes Container Factory, it's actually slower. And this doesn't make a lot of sense initially. We had to dig into it to find out why. Because if you think about this, where we're using the containers, the container factory, the Kubernetes Container Factory is not really involved in this path, except for one thing. in the Kubernetes, in the second configuration here, the Kubernetes container factory is actually extracting the user logs for us, versus in the Invoker agent where it's not. And what's happening here is, even though the log processing is asynchronous, we push it off the path, it takes a really long time for Kubernetes to get those logs out of that container and from the Invoker to process them and forward them. And so the load balancer thinks the container is idle. The answers come back, it thinks it can reuse that Invoker in that container again, but it's still loaded down, extracting logs from the last 10 function invocations that have come to that container. So that's something that could be fixed by modeling in our load balancer, or ideally it could be fixed by improving our log extraction or Kubernetes log extraction capabilities. Okay, the second thing I want to look at is throughput results. And so here the workload is slightly different. We're again running no op actions, but what we're doing this time is running as many non-blocking invocations of this trivial action as we can on the system. And so I'm showing normalized throughput, where higher is better, so we have 1 and things less than 1. And here, again, the two Kubernetes container factories do slightly worse than the Docker container factory. And this is primarily due to the higher log extraction latency, preventing container reuse, loading down the system, and reducing overall throughput. So the key takeaways from this, first of all, the higher cold start costs do matter to us. Our caching is fairly effective, but even if if we're going to have some cold starts, we care, and we want to make those as short as possible. And there's a real latency impact for those for short-running function. And the second thing, which was a surprise to me, is that this log extraction path actually mattered a lot. So we have some work going on now to try to understand how to better optimize our log extraction and our logging architecture on Kubernetes to try to get rid of that problem. So we really want to be able to use the Kubernetes container factory to take advantage of the much larger pool of containers that could be managed by the Invoker, and also to fit more naturally into the cluster scheduling. Okay, so that's sort of our dive through how the OpenWhisk core works and how this hot path of invoking functions. What I do now is shift gears and talk about serverless composition of serverless functions and give you a taste of that. And so this is a project that's being driven out of research, and in research we like to dream big. And so what we're really trying to do here is rethinking the entire cloud programming experience for the developer. And we're coming out thinking about, we're programming a cloud computer. Can we make this thing look more like a computer for the programmer? Can we build a computer-like facade over this distributed system and do this by just writing actual programs in ways that programmers know how to write them and have good tools to make this be available to help us? All right. So what I'm going to do now is I'm going to do a demo, and I'm going to use a little sample program that we use to do this. And this is something that we use. So the idea here is I'm a developer. I'm doing pull requests. They go into Travis CI, tests run. Unfortunately, tests take a while, and eventually they finish, but by then I've gotten distracted and I've forgotten they've run. And so what this is a pipeline that takes a Travis webhook, runs it through a bunch of serverless functions to process that webhook, get some information about it, and then post the result of my test to Slack to tell me, hey, that test you submitted half an hour ago, you should go look at it now. All right? And this is all up on GitHub if you want to look at it, this Travis to Slack example. All right, so now we'll get out of here and get into the demo. All right, so first of all, I have a Minikube running on my laptop here, and on that I've deployed OpenWhisk using my Helm chart. So I can do Helm status demo, and there it is, it's running, and we can see what pods there are. All right, so there's the control plane pods, the controller, the database, the invoker, and so on. All right, so now what we're going to do is we're going to bring up shell. This is our function shell, and I remember to make this font bigger for you. All right, so the first thing we'll do is just make sure this is working by creating a hello action. So we'll do action, create, hello. Okay, so there's the action we created. Now we can do action invoke, hello. Ta-da, welcome to KubeCon. All right, so it ran the action and we got that answer back. So one thing that's kind of useful as a debugging tool. So now I'm in this shell. This is an Electron-based application. I'm looking at my deployed function. I can actually edit this here. Right? I can hit the unlock button. Now I'm in edit mode, editing my deployed code. So I can say this is live, if I can spell live. Okay, so now we'll deploy that. And if we run it, we should get a different message this time. Ta-da. All right, so this is a useful way to sort of get in and do quick debugging for things. All right, so now what I'm going to do is shift to a slightly to VS Code, because we're going to look at a more interesting example. In particular, we're going to look at this composition, and There we go. Let's get things lined up. So this is my Travis Slack pipeline. The picture on the right over here is a visualization of the pipeline. It's produced by Shell. In a couple minutes, we're going to load this app into Shell, and we'll actually see this visualization live. And over here on the left is the code. So we've written this composition. This is a JavaScript library that lets us use familiar constructs to build out this composition. So here's my pipeline here. And there are several things to notice about this. First of all, I can have local variables. So I can declare a variable, and then I can use that to cache intermediate results in this pipeline and use them multiple times. I have a sequence. I'm composing a whole bunch of actions. So each one of these lines is an action. Some of these are defined externally. So these are functions we're going to define in a couple minutes. Some of them are just pieces of inline JavaScript code, and some of them can even be functions. So here, this particular composition allows me to either get the author Slack information from a database or from a local JSON file for debugging. So at deploy time, when I'm deploying this composition, I evaluate this JavaScript code to build up my deployment artifact. We can get in here, we run this get author Slack information, and depending on the value of this environment variable, we either connect to a database or we connect to a local JSON file. A couple other things to see in here. So one is so that we have, one of the uses of these inline functions is my information coming in here, this P, has an author name in it. It could be in any case at all. My database wants it to be uppercased. So I can write a quick little inline function in JavaScript here that goes ahead and converts that from whatever case it's in to uppercase. I also have try-catch blocks. So here I've got a try-catch block in this line here. And what I'm going to do is I'm going to read in the database. Now, if the author hasn't subscribed to Slack notifications, so they don't want to be bothered by every time there's a Slack request, I'll get this lookup will fail. I'll get an exception, but I'll catch that in the catch block and just turn that into an empty dictionary. Done. No need to write fancy code. Just return that to the rest of the pipeline, and now we know that the author isn't there. Okay, so that's the app. So what I'm going to do now is go ahead and create this app. We'll call it Notify TravisSlack.js. Okay, there it is. So here's the visualization. And it's helpfully telling me, hey, by the way, you haven't deployed these actions yet. So rather than forcing you to watch me type that, I'm going to run a script that will deploy them for me. Okay, so now if we do, oh yeah, I need to put that in the background so it'll actually run. So now if we look at the set of actions, those actions are there. All right, so now we can actually try to run this. So we can do app invoke okay, this should take about 5 seconds or so, hopefully, and I should get a Slack notification that this happened. And it didn't work. What happened? All right, so what happens? We can look at the session flow. Oh, no, it did work. It just didn't. All right. Here's my new Slack notification, but it didn't show up on my window over here. I don't know if it showed up on yours or not. This may be an artifact of being in screen show mode. All right, so here's the session flow. So this is showing that here's my pipeline. The things are dark blue because it actually ran. If we hover over any of these, we can actually see what the values were. We can dive in to look at them. Go back to the app visualization. All right, we can see, look at the results of this. And why there, okay, there we go. Let's get my session flow back. We also have a trace view. So here we can look and see a timeline of the execution of this. So the overall thing took 6.4 seconds. We can look at the various actions. The shading here indicates the hash part is the initialization. The solid part is the actual execution of it. We can look down and go down and look at that. All right, well, this is pretty cool. But as I said, some authors don't actually, some people don't actually care about this, and we've done all this computing to generate a notification that nobody cares about. That seems like a natural thing to fix with some control flow. So let me find VS Code again. All right, so what we're going to do now is we're going to go in here and basically short circuit this out. So we can say composer. All right, so we're going to put an if then else in here, and we're going to say we don't really need a parameter for this because we have things in our local variable. So if author Slack info user ID. All right, so now I need a block. And the way we get a block in Composer is we create a sequence. All right, and we put the rest of our code in there. And this is just plain old JavaScript code. VS Code understands it, so we can indent it. We're done. We can save it. Go back to here. We'll invoke it again. And hopefully, this should actually go through. And the Slack window didn't pop up, but if we look down in here, what did it do? Oh, deploy, right. It wasn't, I need to deploy it. Thanks, Olivier. All right, I need to say app deploy, notify, Travis to Slack. No, app update. Okay, it's good. Now my flow diagram has changed, so that's useful because I actually expected it to change. And so if we invoke it this time, I think it's again going to fail to pop up. But now if we look at the session flow, it went down this path. And now I also have a second sample file for someone who doesn't care about this. And so that happened almost immediately. Because if we look at the session flow, what happened here is we came into the first few steps, we hit that if, and we didn't bother doing the computing to actually generate the Slack message for them. Okay, and again, we can look at the trace and see what happened and all that. All right, so that's the end of the demo. What I'm going to do now is shift back to the PowerPoint and kind of wrap up the talk. Okay, so hopefully what I've shown you is a little piece of our sort of vision for how we can make a more computer-like programming environment from the cloud. We saw we had a desktop development environment that lets me use either my own editors or its built-in editor. I can quickly edit code that's been deployed on the cloud and redeploy it. So I can, just like I changed that little hello message in the first thing, I could stick in a logging printf and redeploy almost instantly. With Composer, I have a library written in a familiar language that lets me have variables, control structures, if then else, try catch, loops, and so on, and use those to actually build a distributed program that's running across a polyglot set of applications. So I forgot to mention this, but I was using JavaScript in Composer, but I was invoking actions that were written in Python and JavaScript. So there's not a restriction about what the actual functions have to be written in. With Shell, we have this tooling that runs locally on your machine and gives you a real compelling environment. It has visualizations to support what you're doing, but it also really smoothly integrates into the command line environment with your code editors and just your normal workflow. In terms of, to wrap up with ongoing work, around OpenWhisk and Kubernetes, we're doing a lot of work looking at scalability and performance as we sort of are in the process of taking IBM functions and moving that to be on top of Kubernetes. We're actively working on some enhancement of the Kubernetes container factory-based invoker, along with partners at Red Hat who are really driving some of that work with their OpenShift work. Looking at larger container pools, more options for scheduling and caching policies, and really trying to get a fuller integration with the Kubernetes scheduler. We'd like to do a better job of exploiting Kubernetes deployment and management capabilities to actually simplify the task of operating OpenWhisk. And one thing I've been looking at personally is looking for a smoother developer transition between function as a service and Kubernetes deployed microservices. So once we have everything OpenWhisk running on top of Kubernetes, there doesn't really need to be a sharp distinction between what's a function and what's a container and what's a microservice, and sort of trying to blend that together to make it easier for the developer to go back and forth between those. Composer and Shell, we're really excited about this. We think this is potentially a major step in the evolution of the cloud developer experience. There's a lot of active research going on there in development and so on. In terms of, just to wrap up, I'd like to encourage people to try to get involved with this. Everything I've shown you today is open source. OpenWhisk is obviously, but also Composer and Shell are as well. And so here's some URLs for web pages and GitHubs and Slacks if you're interested in anything that we've shown today. So thank you very much, and I'll be happy to take any questions if people have them.